Hey guys, how you doing? This is Mr. Lee with a video lecture on 10.2, creating a confidence interval for a population mean mu. So there's two major parameters that we're chasing. We're either chasing a mu, a population mean, or we're chasing a p, a population proportion. So in this case, we're chasing a mu, so obviously we're going to sample from a population. We're going to just take one sample to start. Okay, later on we'll talk about taking two samples, but right now we're just going to take one sample and we gather the data from the sample and we get an X bar from that sample. So we know that X bar is an unbiased estimator of mu, and now we have to figure out, well, how do we calculate the margin of error for our confidence interval? Okay. So after this section, you should be able to construct and interpret. Remember, there's two parts. You have to be able to interpret stuff in context, but construct the interval and also interpret the interval for a population mean in context. Determine how big should n be in order to correlate to a particular level of confidence. So what is the critical, how does n how do we calculate how big n has to be? Okay. Describe how the margin of error of confidence interval changes with the sample size and the level of confidence, and also determine sample statistics from a confidence interval. Okay, so first let's talk about Z star. So we learned in the previous section that we have some point estimate here. So in this case, since we're chasing a mu, our point estimate is going to be our unbiased estimator X bar, the sample mean from our one sample. And then it's going to be plus or minus this entire right side. This entire right side is going to be called the margin of error, or the ME. Okay. Now the ME has two parts to it. It has Z star, and then it has sigma over root n. Let's talk about sigma over root n. Well, sigma over root n is just the standard deviation of the sampling distribution of X bar. Okay. Sigma, this part of sigma over root n, sigma is the true population standard deviation. So it's how the entire standard deviation, the distribution of the entire standard deviation, how spread out that is. Okay, and then that's what this side is. This component here, Z star, is just a Z score. It's a critical value. And the reason why we put a star is we're saying it's a very specific critical value that is it's related to whatever confidence level we choose. So once we know the confidence level, we'll be able to figure out, well, what is the Z-score for that confidence level? Okay, so I want to talk more about that in just a moment, but let's go back to this. If you think about inference for mu, right, we're trying to estimate what mu is. We don't know what the population mu is. Are we going to know what the population sigma is? If we don't know what the true population mean is, are we going to know how spread out the data is? Probably not. Okay, so in 10.1, this is a very unrealistic expectation for us to know what sigma is. So today, in today's lecture, we're going to show, well, what are we going to use instead of sigma, and how does that change everything? Okay, but before we get into that, let's just talk about Z star. Okay. So in our first example, we calculated a 95% confidence interval. So there's our confidence level, 95%. Okay, so we use this formula. It's an estimate plus or minus some critical value times the standard deviation of the statistic. So this is what I want to hone in on, this Z star, this critical value. This Z star is determined by what our confidence level is. So at first we said, okay, it's a 95% confidence level. Okay. Well, Z star refers to the critical value that relates to that particular confidence level. So how do you calculate Z star? Okay, well, it's actually not 2. The critical value for 95% confidence is not 2. It's close to 2, but it's not 2. Well, where did we get 2? We just used the 68, 95, 99.7 empirical rule, which is really like a rule of thumb. It's not an exact law. Okay, so now let's actually calculate the exact Z star. Okay. So what is the Z-score? What is the true Z-score for a 95% confidence interval? Well, to calculate that, go ahead and just turn on your calculator, go to second vars, which is your different distributions. So go to distribution or second vars. Scroll down to inverse norm. Okay, and then what is the area under the curve that contains 95%? Well, 95% of the data, it goes out here and it goes here, right? But when we're doing inverse norm, so when we go out here, we want to know what's that critical value. It's not 2, but what is it? Well, when we do inverse norm, it's calculating the entire left tail, not just like this interval, this critical value for this interval that we want. So instead of using 95 for the area, we're going to use 95 plus this 2.5% here. So we're going to use 0.975 for area. Press enter, mu is 0, enter, sigma is 1, enter, paste, enter, and what do you get? You should have gotten 1.96, okay? Let's do the same thing for a 90% confidence interval, okay? So again, second distributions go down to inverse norm. So not 0.90, but 0.9 what? Well, if 90% is in the interval, how much is in the left tail? That leaves 10% for the two tails. So there's 5% in the right tail, 5% in the left tail. So that would be the area you would enter is 0.95. Okay, and what's your critical value? 1.6449. Okay, so you can round that to 1.645. What about the critical value for an 80%? And I don't have to give you these beautiful numbers. I could say, like, what if we want like a 32% confidence interval or a 67% confidence interval or whatever? You would know how to calculate it. Okay. So there are your z-scores, your specific z-scores for specific confidence levels. So there are your z-stars, right? So notice that for 90%, I put 1.645 or 1.644. That's because sometimes the authors will just truncate. Instead of rounding, sometimes they'll just truncate, which means they just chop off everything. So if on your AP exam you see 1.644, don't freak out. It's perfectly acceptable. You're going to end up getting the same answer. Just use whatever they give you, okay? If they don't give you anything and you have to calculate the z-score, just use 1.645 or 1.644. Either one will work. Okay, so now that brings us to, let's just formally name what our first confidence interval is called, or what our first procedure is called. First procedure is called a one-sample z-interval for a population mean mu. Okay, one sample because we literally only took one sample from the population, so it's one sample. Why is it called a z? Well, because we are using z-star because we're assuming we know, we're not assuming we know the true sigma. Okay, so in this unlikely event that we don't know mu, but we do know sigma, okay, we're going to calculate what is called a one sample z interval. So interval. So before we go any further, go to your calculator again and maybe press clear if you want to. Press stat. Okay, then scroll to the right. Remember, we always use stat edit for our lists, but that's not what we're doing. So scroll to the right to tests. So stat tests. Now there's a whole long list of tests in here. There's a z-test, then a t-test, then a two-sample z-test, etc., etc. Those first 6 are all significance tests or hypothesis tests. That's what we're going to learn in subsequent chapters, okay? Right now, scroll down to 7, number 7 on your calculator. 7 should say z-int or z-interval. That is your one sample z-interval, okay? Scroll down to 8, t-int. That's what I'm teaching you today. Number 9, two sample z-interval. That again is a z-interval for a mean, okay, when we have two samples. We haven't gotten to that yet. Okay, scroll down to A, the letter A. What is this? One prop z-int. What do you think that is? Prop stands for proportion. So a one proportion z-int is when you get one p-hat instead of an x-bar. So one prop z-int is like this, but when you're chasing a p, not chasing a mu. Okay, but you do know the true population standard deviation. Okay, so you should have been thinking to yourself, well, what if we don't know? Well, now what do we do when we don't know sigma? Because that is obviously what I've been hinting at. That is what today's lecture is on, okay? So if we don't know what sigma is, well, what are we going to use? we're going to use SX, or the sample standard deviation, the sample standard deviation. What does that mean? That means, remember, we took one sample from the population? Well, we can measure the sample mean, the X bar, and the SX from that sample data. So this is not going to be sigma, this is going to be SX over root n. Okay. Oh, actually, I'm getting ahead of myself just a little bit. One other thing before we get to the t, before we get to what I'm talking about today, is this. We can also use this margin of error, okay, because remember, this whole right side is called the margin of error. We can use this margin of error to solve for n. Okay, the type of question you'll get is, well, what if we want a margin of error of, whatever, 10% or 1% or 5 or whatever. They might not even give it to you in percent form, right? In the homework problems, they didn't give it to you in percent form. But they'll say that the margin of error is some fixed value, right? Then what you're going to do is you're going to just solve for n. You'll know what the z star is. They'll give you the sigma. They'll give you the margin of error. And then you just solve this equation for n. Okay. Okay, so now let's get to our lecture, and here's an example. I'm going to skip the example. It's right in your textbook. It's just like, can you solve for n? It's just a straight up algebra problem. So here's our real lecture today. Okay, so if you don't know sigma, you're going to use SX, which is the sample standard deviation, the standard deviation of that one sample, not the sampling distribution, but of just that one sample, right? Okay, so notice that this new statistic does not have a normal distribution. Now you're looking at this going, wait a second, Mr. Lee, that looks like a normal distribution. Okay, well, it is a close cousin of the normal distribution. It is a family of distributions called the t distributions, or what I actually learned it as, and what it's really known by, is called the student's t. Funny story. Why is it called the student's t? The guy who came up with this inference procedure, the t distribution, was a brewer. He was a guy that made beer at Guinness Brewery. And he was always trying to use statistics and use math modeling to figure out how to make a better version of Guinness beer. And he created this thing, and he published this thing called the t statistic, or the t distribution. And he published it, instead of using his own name, he just wrote the word student, okay, when he published it. So that is why it's called the student's t distribution. Okay, so the student's t is closely related. It's like a close cousin. It's like the first cousin of the z distribution, or the z distribution is the standard normal. It's a close cousin. Well, what is different? Well, this simulation data really shows you what is different between the t, the student's t, and the z. What's different? Well, the z has less variability. Okay, it has a lot less variability. The student's t is quite spread out, meaning there's more density in the tails. It's hard to see in this diagram, but it's shorter. So it's kind of wider and shorter. So there's much more variability in the student's t. Okay, but notice that it's also unimodal and symmetric and centered at the same thing as the standard normal. Okay. Remember I told you that the t distributions are a family of distributions, right? There's infinitely many t distributions. So which t distribution are we going to use? Well, that depends on the degrees of freedom, the DF. Okay, so how many degrees of freedom are we going to use in AP statistics? We're always going to use DF equals n minus 1 for the student's t. Okay, DF is equal to n minus 1 for the student's t. Okay, so let's say that we have an example where our sample size n is equal to 12. Well, how many degrees of freedom are we going to use? N minus 1 is 11. So we're going to use the t distribution where the degrees of freedom is 11. Okay, so what you're going to do is write t subscript 11. Okay. All right, so this diagram just shows you that as n increases, or as our degrees of freedom increases, the student's T model starts to look a lot more like the standard normal. Okay, so as df approaches infinity, okay, the student's T approaches the z, okay, the standard normal. That's a typo. We're going to use table C, not table B, but table C as in Charlie. Okay. So how do you use table C? Well, table C helps us determine what is the critical value. What's the T star that goes along with a particular confidence level? Okay, so in the row, you're just going to find which degree of freedom you're using. So df equals 11. So you go across this row and look at the bottom. Don't even bother with the upper tail part. Don't bother with the top part here. Just look at the bottom. It'll tell you what's a 90, 95, 96, 98% confidence level. Just let's go to the 95%. And then just cross-reference that, and we see that the T star that correlates to a 95% confidence level is 2.201 when we're using 11 degrees of freedom. Okay, whoops. Okay, so this thing here, because we're not using sigma over root n, okay, we're not using the standard deviation of the sampling distribution of x bar, we're using Sx. Sx is an unbiased estimator. Sx is an estimator of sigma. So again, now we're introducing more error. So this whole thing is called the standard error. Why is it called the standard error? Because we're introducing more error or more variability. So now at the bottom of this slide, you can see x bar plus or minus t star times Sx over root n. That is your one sample T interval. Go back to your calculator, turn it on, go to stat tests and scroll down. What number, which one is this? Which inferential procedure is this? This is number 8, your T interval. Okay, T interval, your one sample T interval. Don't forget to check your conditions, RNI, random, normal, and independent. And here's an example, okay? Here's a really nice example, okay? We don't meet the normal distribution, okay, requirement or condition. Since the sample size is small, n is less than 30, we know the central limit theorem doesn't kick in. CLT does not kick in for AP stats unless we're at 30 or greater, right? So now we have to check whether it's reasonable to believe that the population might be normal. So examine the sample data, and we're going to use that as sort of an estimate of the population. So let's take a look at the sample data, okay? There's 3 different graphs here, okay? What do we see? Well, the most important of these 3 is probably this one right here, which is called the normal probability plot. The normal probability plot is when you're using your calculator to graph, okay, if you go to second stat plot and just go to your first plot, the normal probability plot is the last one. See how there's 6 different plots you can choose from? Okay, it's the last one. Okay, when it says type, it's the last one. What are we looking for? We're looking for linearity. Okay, that's approximately linear, so we're like, okay, that'll work. So we're using 19 degrees of freedom. So our critical value that corresponds with 19 degrees of freedom is 1.729. By the way, can you use your calculator for this? Sure you can. Go to second distribution, and instead of inverse norm, just go to inverse T. Inverse T. Okay. Just remember that inverse T, like inverse norm, is a left tail calculation. Okay, it's a left tail calculation. Okay. So instead of 90, we're going to use 0.95. and the degrees of freedom we're using is 19. Okay, let's paste that. And we get 1.729, which is the same thing you would get from the table. Okay, so there's our interval. There's two different ways of expressing your interval. I'm sorry this slide got all jacked up, but 306.32 plus or minus 14. So that is one way. That's a valid way of writing an interval. Another more common way is just to write the lower bound and the upper bound in parentheses, okay, separated by a comma. Here is your interpretation. Remember, I told you to memorize the interpretation. We are 90% confident that the interval from 290.32 to 320.32 megavolts captures the true mean tension in the entire batch of video terminals produced that day. Okay, so here's the thing. Can we use a statistical procedure if we do not specifically meet all the conditions, the RNI? Yes, we can. Darn it. I was hoping we could just say, nope, conditions not met, we're done, and stop. Can't do that. Okay, we still go on with the test or the procedure, the calculating the interval, because these inferential procedures are all robust. Okay, what does robust mean? It means that even if one of the conditions is not, specifically met, okay, we still get a very good calculation. We still get a very accurate result, okay? That is the definition of robustness. Yes, that's important. Yes, you need to know that. Okay, so using one sample t procedures, the normal condition. If the sample size is less than 15, use t procedures if the data appear close to normal, roughly symmetric, single peak, no outliers. If the data are clearly skewed or if outliers are present, I wouldn't use the t. Okay, when the sample size is at least 15, the t procedures can be used except in the presence of really bad outliers or strong skewness. And then for large samples, if the t procedures the t procedures can be used even for skewed distributions when the sample is larger than 30, okay, greater than or equal to 30, okay. All right, guys, that's all we have for you. I will see you in the next video.